where our critical points are. Critical points are where the first derivative is 0. And so let's factor this. I can factor out a 12x squared, leaving me a 2 minus x. And I set that equal to 0. And there are two values of x. X could be 0 or x could be 2. So there are two critical points. X as 0, x as 2. So I will want to plot these points, so I need the y-coordinate. Go back to the original. Some people go back to the first derivative, but naturally you'll get 0 because that's where the critical point came from. So go back to the original. There you have 5. And I need the y-coordinate at 2. Put 2 in. That's 5 plus 2 cubed is 8. That's 64 minus 48, right? Because 2 to the 4th is 16, 48. So let's see, that is 16 and 5 is 21. Did I do that right? That's 48. Okay, so I want to plot those points. Notice, because my y-axis is a big number, I need to scale my axes a little differently. So on the x-axis, let me scale 1, 2, 3. But then on the y-axis, let me scale it in 5s. 5, 10, 15, 20, 25. Scale it in 5s. So at 0, y is 5. There is one critical point. And when x is 2, y is 21. 5, 10, 15, 21, right about there. So I have two critical points, meaning I have 3 shape intervals, one for each, one more than the number of critical points. So I want to analyze each shape interval by testing f prime at one point. And I'll conclude something about the shape. So I have 3 intervals. 1, 2, 3. So I have an interval left of 0, between 0 and 2, to the right of 2. So remember why I only have to test one point. Within an interval, it's all going to be increasing or it's all going to be decreasing. It's not going to change its mind. Because if it went from increasing to decreasing, that would create a new critical point, and there are only 2 of them. So each interval has to have the same shape. So let's test f prime of -1. Now all I care about is whether it's positive or negative. Sure, I could go back to my original, but isn't the factored form easier? If I put in -1, that factor is positive, and that factor is positive. I'm multiplying 2 positive factors, so it's positive, and therefore my shape is increasing. How about f prime of 1? Positive, positive. Again, it's still increasing. Now, is this the first time? No, it did happen on the previous problem, and I just didn't point it out. But as long as we're here, let me point it out. Notice that the direction did not change on either side of the critical point. Most of the time it does, but it doesn't have to. Most of the time these are alternating, but doesn't have to be. So don't fall into a trap of assuming, oh, these always have to alternate. Here, how about f prime of 3? That's positive, that's negative. Positive times negative is negative, therefore it's decreasing. All right, so I've squeezed all the information I can out of my first derivative. Now, let's do the second derivative, f double prime. The second derivative is telling me how the first derivative is changing. Do the second derivative. Do your rules again. 48x minus 36x squared. Did I do that right? 24 times 2 and 12 times 3, yeah. So again, I want to set that equal to 0 to solve. And how about if I factor it? Let me factor out a 12, leaving me a 4x. Oh, factor out a 12x, I'm sorry. I can factor out a 12x. Leaving me a 4 minus 3x squared. 3x. 3 times 12 is 36, x times x. Yeah, there we go. And so I set this equal to 0 because I'm asking about inflection points. And there are 2 of them. Remember, an inflection point is where the second derivative is 0. So there are 2. X could be 0, or x could be, is that 4/3? 3/4 rather. 4/3. When x is 4/3 times 3 is 4 minus 4. Okay. And I need these points. Let's do the y coordinate. Put 0 into f. It's 5. So notice that this point, maybe I should use purple. This point is also an inflection point. So yeah, you can have a point which is both critical and inflection. And then let's come over here. Y equals f of 4/3. So that would be 5 plus 8 times 4/3 cubed minus 3 times 4/3 to the 4th. Yeah, you don't have your calculators, so just ballpark it. So that's a little bigger than 1, that's 13. 13 minus 4 is about 9. That's about 9. And so at 4/3, it's right about there, we have a, no, right about 9. So 4/3, 9. So there's an inflection point. So that is giving us 3 intervals. So I have concavity intervals. Over which I'm going to test the second derivative at one point in order to conclude something with concavity. So, left of 0, between 0 and 4/3, to the right of 4/3. So let's take f double prime of -1. Sure, you could plug it into here, but isn't the factored form easier? So that is negative and that is positive. X is -1, so that is a negative factor. And if that's -1, that's positive. A negative times positive is negative, the concave down. And here, how about 1? 1 is in there. And so that would be positive and positive. Positive concave up. And finally, how about 2? Positive, negative. 4 minus 6 is negative. So it's concave down. So let's put all that information together. You see, all in all, I've got 3 interesting points. This guy's both critical and inflection. That's inflection. I guess I could have labeled that. I'm using purple for the inflection. And F2. So let's take a look. These 3 points induce forward intervals. Let's look at it. Let us look at each interval. Left of 0. So look it up on this chart. Look it up on this chart. Here, the shape is increasing. The concavity is down. So what does an increasing concave down curve have to look like? It has to look like that. Now between 0 and 4/3, that lies in the second row here, right? So it's still increasing, but now it lies in the second row there, so it's concave up. Now I have to sketch increasing concave up. Now between 4/3 and 2, that lies in the second row here, so it's increasing. But it lies in the third row there, so it's concave down. So sketch an increasing but concave down curve. And finally to the right of 2, that's the third row here decreasing. And it lies within the third row there, concave down. So what does a decreasing concave down curve look like? Looks like that. Okay? And so here at this 0, 5, that was both a critical point and an inflection point. And does that sort of remind you, you're not surprised at what's you're not surprised at what is happening there. Do you remember your simple cubic curve y at y equals x cubed? Do you remember that also has this shape? Comes in, goes up. So, sure, it's a different function, but you see the shape's the same. Because that there is also both critical and inflection. Just to link this up with business language. Okay. That point at 4 comma 9, 4/3 comma 9. That is an inflection point. And in economics, that's called the point of diminishing returns. And do you sort of see why? Remember, your derivative is the slope of the tangent. So as you journey on the curve from 0 to 4/3, notice that your slope is getting larger and larger and larger. But it reaches this point and the slope starts to turn negative. The slopes are going back down, and finally it heads to 0. Okay. So if you're talking about a profit function, you know, there's where profit is maximized, because that's where your first derivative is equal to 0. And so if f is a profit function, that's where your profit is maximized. But here is the beginning of the end, so to speak, that you're more profitable as you sell from here to here. You're becoming more profitable. And yes, as you sell from here to here, you're still more profitable, but do you see that your profit margin is diminishing? From here to here, your slopes are positive. From here to your slopes are negative. So that's why this is the point of diminishing returns. You're on the way down. Okay, let's take a look at 33. So here we have f of x as x squared e to the x. And let me just remind you, remember, if you just had e to the x, you know, if you just had e to the x, we've talked about what that graph looks like. That's an exponential graph, meaning it's getting big quickly. So when x is 0, e to the 0 is 1. E to the 0 equals 1. And then for these negative x's, remember, a negative power means reciprocal. So 1 over e squared, 1 over e cubed. They're getting smaller and smaller and smaller. And here, they're blowing up. E to the x is getting bigger and bigger. But notice, e to the x is always positive. It doesn't cross the y-axis. So e to the x is never 0. E to the x is never equal to 0, because it's asymptotically going to the x-axis, but it never reaches it. So e to the x alone is never 0. So I just wanted to review that with you. Now let's look at the problem. So I'll leave some space for my drawing, and I come down here. I want my first derivative. Do you see I have a product? I got x squared times e to the x. There's a product. So p prime q plus p q prime. Most of you on the test were okay with the product rule. P prime q plus p q prime. And I want to set that equal to 0 to solve for the critical points. Notice I can factor. factor out an e to the x and an x. Factor out an x and e to the x, which is leaving me here with a 2, and here it's leaving me with an x. So I've set that equal to 0. And so what value is x? Remember, I just said e to the x is never 0. The e to the x part, that doesn't give you any critical points. X could be 0 or x could be negative 2. So we have 2 critical points at x could be negative 2, x could be 0. Well, I need the y coordinate. So plug negative 2 into the original. Negative 2 squared is 4e to the negative 2. Isn't that 4 over e squared? So e is about 2.7. E squared, it's like 5. So that's something a little less than 1. That's a little less than 1. And over here, we've already said when x is 0, 0 squared is 0. So here's what I've got so far. Yeah, so let's scale this 1, 2, 3, 1, 2, 3, 1, 2. Okay, so here, when x is negative 2, y is a little less than 1, right about there. So that's the critical point, negative 2, comma, 4 over e squared. And now, when x is 0, y is 0. There is a critical point. Okay, so 2 critical points give me 3 intervals. It's 2 my shape intervals. Over which I'm going to test the first derivative at one point to conclude something about the shape. So left of negative 2, between negative 2 and 0, to the right of 0. So let's test f prime at negative 3. And so I only care about the sign. So this factor, put in negative 3. You know, e to the negative 3, that's always a positive number. That's why I reviewed this graph with you. E to the x itself is always positive for all x. So that would be a negative times a positive times a negative. But a negative times a positive times a negative is positive, shape is increasing. Now between negative 2 and 0, let's test negative 1. Put in negative 1 and I have negative, positive, positive. It's negative, so it's decreasing. And to the right of 0, let's pick positive 1. Positive, positive, positive. So it's increasing. Okay. So now let's go to our second group. F double prime. Okay, fun. This is a product rule, and this is a product rule also. So let's do a product rule there. P prime Q plus P Q prime. Remember, e to the x is its own derivative. I should have mentioned that maybe. We did talk about this in the first half of the course. Remember, e to the x is its own derivative. So I should have mentioned that again. So looking here, P prime Q plus P Q prime, it is its own derivative, plus. Do a product rule here. P prime, that's a 2x e to the x, P prime Q plus P Q prime. And I'm going to set that equal to 0 in order to find inflection points. So doesn't this add? That gives me 2 e to the x plus 4x e to the x plus x squared e to the x. 2x e to the x, 2x e to the x, it gave me 4. So I can factor out an e to the x, and what I'm left with is a trinomial that I can factor. Or can I? No. Nice. I'm stumbling because I should be able to factor that. And have I made a mistake? Am I going to have to use the quadratic formula? Yeah, okay. You should know the quadratic formula, and I'm gonna have to resort to that. Do you remember back in high school? You studied quadratic equations. Ax squared plus bx plus c. If that equals 0, there's a formula whereby you can find the x's that do that. It's called the quadratic formula. And so x is, there are two choices. It's negative b plus or minus the square root of b squared minus 4ac all over 2a. And so I need to find the x's that are inflection points. I need to find the x's that make that equal 0. And I'm going to have to use this quadratic formula, so that I come out with, I'll do this, negative 2 minus root 2 or negative 2 plus root 2. So that would be like negative 3.4, and this would be like negative 0.6. Yeah. Okay. Let's continue. Hopefully you remember the quadratic formula. So here is our second derivative. We set it equal to 0. Remember, I said e to the x is never 0. So the only way this could equal 0 is if this quadratic is 0. So x squared plus 4x plus 2 equals 0. And so there's where, I thought that would factor, but no. Here's where you need your quadratic formula. X is negative b plus or minus the square root of b squared minus 4ac all over 2a. Which in this case, b is 4, so that's a negative 4 plus or minus the square root of. B squared is 16 minus 4ac. C is 2, A is 1. So 4 times 2 is 8. All over 2a, A is 1. So that's negative 4 plus or minus root 8 over 2. But uh, 8 is 4 times 2, so that's 2 root 2 over 2. So that becomes negative 2 plus or minus root 2. So that gives you 2 inflection points at x would be negative 2 minus root 2, which is about negative 3.5. And also x equals negative 2 plus root 2, which is about negative 0.6. So negative 3.4, 1, 2, 3, 3.4, right about there. I could use purple. And 0.6, negative 0.6, right about there. Okay, and so let's do our 3 intervals. We've got concavity intervals, over which I'm going to test the second derivative. It can include something about concavity. So, left of negative 3.4, between negative 3.4 and negative 0.6, and to the right of negative 0.6. So let's test f double prime at negative 4. And so that would be, that's always positive. So at negative 4, that'd be positive. So it's concave up. Let's go here at negative 2. And at negative 2, that would be negative, concave down. And f double prime of 0 would be positive, concave up. All right, so we put all this together into our picture. Increasing concave up. Increasing concave up. Increasing concave down. Now at negative 2, we're going decreasing, but we're still concave down. Now here at 0, we are 0.6 rather. We are still decreasing, but now it's concave up. And yeah, so I apologize for the quadratic formula. These ended up harder than I expected. So I would have considered it a fair problem if that had been factorable, so you didn't have to resort to the quadratic formula. But there's your picture. Yeah.
For negative 3.4 and negative 0.6, what were the y coordinates of that?
Yeah, I was afraid you were going to ask me that. In order to get the y coordinate, I'd need to take my negative 3.4 and plug it back into my original. Squared, that's like 10, e to the negative 3.4. But you sort of need your calculator for that.
Mm-hmm.
So I knew it was about there.
Okay.
So, yeah, I'm sorry, this was sort of a calculator problem. I had to have your calculators. So, no, I wouldn't give you something like this on the midterm unless that were factorable. I mean, if that were nicely factorable, then the arithmetic would be easy. But the arithmetic here just got kind of brutal.
What was your C value for the quadratic?
Oh, yeah, the C is 2.
Okay.
So, you know, this is A, that's B, that's C. So C is 2. So this was negative 4AC.
Okay, thank you.
So the arithmetic was nastier than I expected. Now, there are a couple of word problems here, but let me say something first. Yeah, so diminishing returns, they're simply asking you for inflection point. But let me say something about the next chapter. compared to what you've been doing, the next chapter's easy. Okay, so this is 5.5. This is called absolute extrema. The word extrema simply means maximums and or minimums, extreme values. So that refers to maxes and minimums. Extrema. Well, so far, we've been doing these kind of problems. We've had a couple of cubics sideways S, you know. We've had these kind of problems where there was only a relative maximum. There was a relative max. Because it's taller than all of its neighbors, that's why it's relative, that's why it's maximum. But it's not absolute, because over here, these y coordinates are just getting bigger and bigger and bigger. And here was a relative minimum. Minimum because its y coordinate is shorter, smaller than its neighbors. But there is no absolute minimum on this graph because it just keeps on going downward. Okay. Now, this is perfectly fine and true mathematically, but in the real world, generally you have got constraints that limit how much you can produce, that limit how much you can sell. So, in practical terms, this is what 5.5 is about. 5.5 limits the x between a couple of values. So, in practical applications, how much you can produce, how much you can sell, there are limits. You can find an A and a B so that x is strictly between A and B. In that case, if you restrict a continuous function to a closed and bounded interval, there will be absolute extrema. And let me write that. If you limit a continuous function between a closed, bounded interval, there will be absolute extrema. And so let me do an example. Let's take this one here. Let's say that I am going to limit myself from let's say from here over to here. So I'm no longer interested in the whole black graph. I'm only interested in that part of the graph which is above the purple interval. In other words, it starts right about here and it goes up to right about there. So I'm not interested in the whole graph. I'm only interested in the purple piece. That purple piece guaranteed will have an absolute minimum and an absolute maximum. So let's just eyeball it. Do you agree with me over here? This B, that's the tallest purple point. So this B comma f of B, that is my absolute ABSOLUGE. That's my absolute maximum. And now, where is my absolute minimum? Oh, this relative minimum is now an absolute minimum. So notice in this particular case, one extrema occurred at an endpoint, and the other extrema occurred at a critical point. You can have all combinations. Your extrema might be at both endpoints, or your extrema could be at critical points. You don't know. It all depends on where you draw the A and B. If I drew the A and B over here, there'd be different extrema. So here is the result. If you limit a continuous function between a closed bounded interval, there will be absolute extrema. If, let's call it F, is continuous on an interval A to B, then absolute extrema will be at, there are two places. One, at the endpoints. F of A and or F of B. That's a possibility. The second, they could be at critical points in the interval A to B. Those are the two places that absolute extrema can occur. And the good news is you don't have to graph. These guys you don't have to graph. Just numerically. Check out. F of A, F of B, and F of C where C is critical in the interval A to B. Those are the only places that extrema can occur, either at endpoints or at a critical point in the interval. And you don't have to graph the thing. Just plug them into F and see what's the largest, what's the smallest. So in a sense, these problems are a whole lot simpler. So come Monday, we'll take a look at some examples of that. So finish on 5.2, look at 5.5 for Monday, see you Monday.
What's that verb after numerical?
Check,
Okay, thank you.
check it out.
Yeah.